Hello physicists and welcome. In this session we'll be covering momentum 3. Make sure you viewed momentum 2 before watching momentum 3. Our learning objectives here are: I can calculate impulse, force, time, or change of momentum given 3 of the values, and I can express impulse and momentum in algebraic and graphic forms. Let's get started. A quick review of impulse. Remember that an impulse is a force applied for an interval of time. Our algebraic expression is J. The symbol for impulse is force times time. The units for this are the kilogram meter per second, the same as the units for momentum. And our unit for force is called the Newton. If we unpack that, we know that it's the kilogram meter per second squared. And for time, it's second. If we multiply these two units together, we get a kilogram meter per second. And an impulse causes a change in momentum. We can express that algebraically as our impulse is a change of momentum, and a change of momentum is the change in the quantity mass times velocity. And anytime we have a change, it's our final value minus our initial value, including for momentum, velocity, all kinds of things. Hey, we can express these a couple of different ways. Our final momentum is our initial momentum plus that change in momentum, or another way of expressing it is our final momentum is our initial momentum plus the thing that causes the change of momentum, impulse. Putting this all together, we could say that our impulse is equal to a force times a time, which is our change in momentum, which is a change in the mass or a change in the velocity over some time. Or another way of expressing it is our final momentum minus our initial momentum. And remember that these are all equivalent. They've got equal signs between them. So one can replace the other. We could say that impulse is equal to change in momentum. We could say force times time is equal to our final momentum minus our initial momentum. Let's take a look at some of the relationships that we can get from those equations. Remember, we have direct or inverse relationships. Direct relationships are when the two variables increase or decrease the same. So they're found when the variables are on opposite sides of the equation. And an inverse relationship is when the variables are on the same side of the equation. An inverse relationship is if A goes up, B goes down, or vice versa. A direct relationship, if A goes up, B also goes up, or we could say it is if A goes down, B goes down. Put that arrow in there. Hey, let's take a look at the equation. What does that end up telling us? Let's look at things that are on opposite sides of the equal sign. So if I were to increase my force, keeping time the same, that means my impulse would increase. Could also say that my change in momentum would increase. It could say that my change in velocity would also increase. Let's look for examples of inverse relationships when the variables are on the same side of the equation. Hey, I see that force and time are on the same side of the equation. So if I were to say that impulse remained the same, that would be the same as saying, hey, our change of momentum is staying the same. And force were to increase, that means that time would need to decrease, or vice versa. If our force decreased, our time would need to increase. Hey, and just a reminder that our impulse, force, velocity, and momentum are all vectors. Those are quantities with both magnitude and direction. We're going to analyze some situations we had in the last video a little more thoroughly here. You remember we had the car accelerating from 0 to 20 meters per second. The mass of our car was about 800 kilograms. What we'd like to know is how much force is needed if the car takes 5 seconds to speed up. And I'm looking for force, and I'm given time, and I know there's a relationship that, hey, force times time is equal to an impulse, which is equal to my change in momentum. Hey, previously, we saw that the change in momentum was, remember, which is our mass times our change in velocity, was 16,000 kilogram meters per second. Refer to the previous video if you're not sure how to get that. Let's do a little equation solving now. Hey, I see my force times time is equal to 16,000 kilogram meters per second. So that means my force is going to be equal to 16,000 kilogram meters per second divided by time. Notice I've divided each side of the equation by time. I know that this is the same as 5 seconds. Let's do the math here. 16,000 divided by 5 is 3,200, and our unit for force is the Newton. And this is speeding up to the right, so this is going to be a positive value. Let's take a look at the other example we had. Hey, we had an airplane landing on an aircraft carrier deck. The mass of the airplane was 4,000 kilograms. It was initially flying at 70 meters per second. We've got to stop that. Okay, so notice here that our change in velocity is actually a negative number, minus 70 meters per second. So it tells us our change in momentum is also going to be a negative number. Okay, so now we want to know how much time until the plane stops if a force of 112,000 newtons pulls on the airplane. Just as a reference, newtons are our scientific unit of force. We're more used to the customary unit of pounds. It takes about 5 newtons for 1 pound. Again, in this case, we're looking for time. So we're going to, hey, look at this. Force times time is equal to an impulse is equal to our change in momentum. From our previous video, we found that our change in momentum was equal to minus 280,000 kilogram meters per second. Remember, our change in momentum is to the left. It's slowing down. So dividing each side of these equations by force to get time by itself, hey, our time is going to be equal to our change in momentum, which is our impulse, 280,000 kilogram meters per second. Remember, that is a negative. Okay, we're going to divide it by the force. Now, the force is also to the left, so we're going to indicate that with a negative number, 112,000 newtons. Sorry for the writing. Okay. Hey, I take minus 280,000, divide that by minus 112,000, and I get negative divided by a negative is a positive number, 2.5 seconds. Have you ever seen airplanes land on aircraft carriers? That's about the amount of time from they initially touch down to when they stop, about 2 to 3 seconds. Let's look at another example. Hey, in this one we have our soccer ball rolling to the right at 10 meters per second. Our young soccer player kicks the ball and it starts rolling to the left. Hey, notice something here that we start with a positive quantity and we end up with a negative quantity. So our change in velocity in this case is our final velocity, and we're calling left negative, minus 8 meters per second. We have to subtract the initial value, minus our 10 meters per second. So how much did the velocity change? It changed minus 18 meters per second. It went from going 10 meters per second to the right to 8 meters per second to the left. So we have a negative change of velocity, which looks like which will cause our change in momentum to be negative as well. So the question we have to ask here, or answer here, is, hey, we've got a player can exert 36 newtons of force on the ball. What's the contact time with the ball? Hey, again, we'll take a look at, hey, force times time is equal to our impulse, okay, which is what causes our change of momentum. You can go back to your old notes to find out how we got this value, but we see our change of momentum was minus 7.2 kilogram meters per second. Hey, again, isolating for time is going to require us to divide by force. Sorry about that. Our time is going to be equal to minus 7.2 kilogram meters per second. And we have to divide by the force. Now notice our young kicker is kicking to the left, so our force is going to be negative. So minus 36 newtons. A negative divided by a negative, 7.2 divided by 36 is 0.2 seconds. So that's how long the ball was in contact with our our soccer player's foot. Let's look at our follow-up question here. Hey, if the contact time could be increased to 0.25 seconds, how fast would the ball be kicked? One of the things that's often talked about in sports is follow-through. And what does follow-through do? It actually increases contact time with baseball, with tennis, and in soccer. If you have a good follow-through, rather than just punching it, if you end up following through, you can stay in contact with the ball a little bit longer. Let's go and figure this out. So to figure out how fast the ball would be kicked, we're looking at the change in momentum, which is caused by an impulse. Our impulse is the product of both the force and the time. Hey, in this case, our force is still minus 36 newtons. Our player is kicking just as hard, but we're increasing the contact time to 0.25 seconds. So let's see what the impulse would be here. So 36 times 0.25 tells me that it is minus 9 kilogram meters per second. Is our change of momentum. Our final momentum is our mass times our final velocity, which is going to be equal to our initial momentum plus our impulse. Let's put in some numbers there. Our initial momentum is our mass times our velocity, so we get 0.4 times 10, that's going to be 4 kilogram meters per second. Sorry about that. Meters per second. Hey, we know our impulse is minus 9 kilogram meters per second. Hey, so our final momentum is minus 5 kilogram meters per second. So our mass times our final velocity is equal to minus 5 kilogram meters per second. Let's go ahead and we're going to divide each side by mass to get our final velocity. See, our mass is 0.5 kilograms. So our final velocity is minus 5 divided by 0.4. You get, what is that? Minus 12.5 meters per second. So by improving our form without getting any stronger, our soccer player can now kick the ball at a speed of 12.5 meters per second, or velocity minus 12.5 meters per second. That's going to the left. Let's practice some more changes of momentum by algebraic equations. All right. Hey, so we just saw that our final momentum is a result of our initial momentum and some type of an impulse. So we go back to our equation here, that our initial momentum plus that impulse, which we can also call our change of momentum, is equal to our final momentum. Hey, so we have an airplane here. We'll say that it has a mass of 5 kilograms. The initial velocity is 30 meters per second. The engines are going to produce a force of 50 newtons. Remember, that's our unit of force is the newton, and we're going to turn those engines on for 2 seconds. We want to find out what our final momentum is. Let's go through this. Hey, our initial momentum is equal to our mass times our initial velocity. Let's go with that. We have 5 kilograms times our initial velocity of 30 meters per second is going to be equal to 150 kilogram meters per second. Our impulse, J, our impulse is our force times our time. In this case, 50 newtons times 2 seconds gives us, again, 100 kilogram meters per second. Add those up, and our final momentum is 150 plus 100, 250 kilogram meters per second. Hey, if we also had the question about, hey, what's that final velocity? We know that our mass times our final velocity is equal to our final momentum. So we could say our final velocity is equal to our final momentum divided by mass. Let's go and do a little work at this. 250 kilogram meters per second divided by the mass of our airplane, 5 kilograms. And after we've turned the engine on, 250 divided by 5, 50 meters per second. Another way of expressing that is by a graphic form. Hey, anytime we multiply two numbers, we can also look at that as being the area of a rectangle in this case. So I'm going to take a look at calculating our momentum by graphic area. And let's see, the area of our rectangle, I have a height based off velocity and a base based off the mass. And we're going to make sure that we include our units when we look at both our axes and our area. Going back to the same values we started off with, we have a mass of our airplane, 5 kilograms, and an initial velocity of 30 meters per second. I'll create this graph. Hey, so I've set up my axes on my graph. Horizontal axis is mass in kilograms, vertical axis is velocity in meters per second. So I could accommodate these values. Hey, so I have 1, 2, 3, 4, 5 kilograms is the mass of the plane. My initial velocity, 30 meters per second. So I can represent that as this rectangle right here. And if I look at the area of this rectangle, height times base, 30 times 5, that's 150. And what's the area of this? It's meters per second times kilogram, a kilogram meter per second. So graphically, I can represent the initial velocity this way, as the area of this rectangle. We can use the same technique of looking at the area of a graph to indicate our impulse, because our impulse has two factors, force and time. So let's go ahead and prepare our graph for that as well. For the impulse that the airplane received, we have a force of 50 newtons and our time is 2 seconds. I'm going to place time on the horizontal axis and force on the vertical axis. So I've set up my graph with the axes, units labeled along with the divisions. And I'm applying this force, and the force remains constant at a constant 50 newtons for all 2 seconds. So up to here for 2 seconds. So I can represent the impulse as this rectangular area. You probably see that if our force was varying over time, we'd end up having slightly different shapes. But we'll say that our force here is being applied constantly for those 2 seconds. Got a pretty good idea of that. So the area of this rectangle, 50 units high, 2 units wide, 50 times 2 is 100. We have newtons times seconds. We've seen that earlier, that is also a kilogram meter per second. Let's go ahead and put these all together. Hey, just like before, when we were looking at our final momentum, it was the sum of an initial momentum and our impulse. We can do that graphically as well. So I've transferred the graphs we've created before. The airplane initial momentum, 30 meters per second and 5 kilograms. Our force of 50 newtons applied for 2 seconds. Our initial graph has an area of 150 units. Our second graph, 100 units. Let's go ahead and get caught up. Just remember our values here to start off with. All right. And so 150 plus 100 would tell us what our final result would be. 150 plus 100 is 250. Right, so 250 kilogram meters per second. Our final graph will be a momentum graph, so we know we'll have mass on this axis and velocity on the vertical axis. Hey, our mass doesn't change. The airplane still has a mass of 5 kilograms. 5 in kilograms. So we know it's still going to be here. Okay, so we could end up saying or asking ourselves, hey, how high would this rectangle need to be if it has a base of 5 kilograms to have an area of 250, whatever our units are. And we can pretty well see that has to be 50. So 10, 20, 30, 40, 50. So this rectangle, hopefully you can see this, it's made up of really 2 rectangles. Our initial momentum, our impulse, just kind of cobbled together, 20, 30, 40, and 50. The area of this rectangle represents our final momentum with a width of 5 kilograms and a height of 50 meters per second. Hey, our final graph here shows our mass 5 kilograms. We have to have a total momentum of 250 kilogram meters per second, so we need to have a velocity of 50 meters per second. This technique works for positive and, if we were below the x-axis as well, negative areas as well. Okay, so as a final check, let's go back to our learning objectives. Can you now calculate impulse, force, time, or change of momentum given 3 of the values? And can you express impulse and momentum in algebraic and graphic forms? That's it for now.